Welcome back to another episode of apparently I can't fucking work XSplit because I recorded this video. It didn't. I thought I was recording the video. Went on for 20 minutes, and it turns out it didn't fucking record. So thanks XSplit. Now that that's out of the way, let's talk about chemical potential energy and enthalpy changes of reaction. Now, we can define potential energy as energy due to position or composition. So, for example, gravitational potential energy is energy just due to the position. As we can see here, uh, nature generally tends to the path of least resistance, and it'll want to be in as low energy potential. It'll want to have the lowest amount of potential energy as possible. Um, so, as a result, uh, you know, things can happen if you put them up somewhere. So, if you raise a brick and you let go of the brick will fall because that's how nature works. Because you have built up gravitational potential energy, but since you want to minimize the amount of potential energy you have in a system, you drop it, it'll drop down to the ground where it has no potential energy. And in an analogous way, in an analogous way, we can describe the same thing with chemical potential energy. It's energy due to composition. So, just inherently different chemical structures are more stable than others. Um, as you go later in the course, you'll have an idea of what structures are and aren't more stable than others. Um, Now that being said, uh, that's a big determining that is quite a big task in and of itself, and you'll probably be studying it. If you take chemistry through second or possibly third year university, just because that's just a big question to ask. Um, with that in mind, now for some stupid reason, the chemists of the world have decided to not use the term chemical potential energy, which I think is personally a lot easier to understand conceptually. They've decided to use this stupid term called enthalpy, which is even more confusingly given the letter H to denote it. Why, you might ask? Well, God knows why. I think it's something to do with the German scientists who, worked on this shit. But to be honest, I am equally as clueless as you are as to why this is given the letter H. Anyway, basically, enthalpy, it's analogous to chemical potential energy, and enthalpy change of reaction is just given as the H of the products minus the H of the reactants. Uh, Put more, in terms you might understand, it's the potential energy of the product compared to that of the reactants, and it's the difference between final and initial states. Pretty simple, right? And then you got some little blurb on standard enthalpy changes. Basically, uh, standard standard enthalpy change is just the stupid. It's just the enthalpy change measured at standard conditions, i.e., room temperature, room pressure, 1 molar concentrations. Pretty. I mean, I don't know. There's much. Basically, how you do it in a lab, in a normal lab. That's really all there is to it. And in accordance with the first law of dynamics, this change in enthalpy that we can measure, uh, this change in enthalpy, we can actually measure it by the amount of heat something gains or loses when, for example, with combustion, we can measure the enthalpy change of, combustion by, burning it and, I don't know, heating something up and then using Q equals MC delta T to determine the amount of energy. And then we just remember that the first law states that chemical potential energy the chemical potential energy lost is equal to the heat energy gained. And yeah. Now, in terms of enthalpy changes, there are two types of reactions dependent on does heat exit the system or enter the system, and those are exothermic and endothermic. Exothermic meaning heat exits the system, so exo exit, and endothermic meaning it enters the system. Endothermic enters the system. I don't know. That's how I remember it. I don't know. You find some other memory device that works for you. But anyways, basically, for an exothermic reaction, the enthalpy of the reactant is more of the products because it lost potential energy and you typically gained kinetic energy or electrical energy. The system basically you put energy into the system as a result of losing the potential energy, and this is typically denoted with a negative delta H. For examples, for some examples of exothermic reactions, we have neutralization, we have combustion, and consider this stupid little diagram here for an exothermic reaction. Uh, the enthalpy of the products, as you can see here, is lower than the reactants since the y-axis is H, and we see that this is a loss in potential energy, or its delta H is negative. These reactants here have more potential energy than the products, and since that's the case, the kinetic energy gained by the system you must have a gain in kinetic energy, and since we usually use temperature to measure this, the gain in temperature must be positive, since we input kinetic energy to make the system hotter, which involves a higher temperature, and the reason it is because we burned something and made those sets of chemicals lose their potential energy. Endothermic reactions are the exact opposite of this. Heat is absorbed by the system, and there's more chemical potential energy in the products than there is the reactants. Again, I don't know, think of it as an analogous to the exothermic reaction is dropping the brick, and the endothermic reaction is picking the brick up. The products have more potential energy than the reactants, so it had to gain potential energy by stealing the energy from the surroundings. So the temperature must decrease in the system. The temperature must decrease. Bond strong in the reactants and the products, and the reactants are more stable, whereas the opposite is true for the exothermic reaction. Yeah. That's about it. Well, there's some more stuff here. Changes of state, melting and boiling. Yeah, this should be obvious to you that it's endothermic because in order to boil a pot of water, you have to put it on a stove, which gets hot. I don't know. That should be kind of obvious, but you'd be surprised um, as to how dumb some people are. Anyways, and we can plot this sort of we can plot phase versus temperature on something called a cooling curve. Here it's a solid. The flat lines are where the phase change is occurring. Then it's a liquid. Here's where the phase change is occurring, and this is a gas. Now, the actual explanation as to why these things are endo and exothermic will make sense when we discover bond enthalpies, and then it will intuitively make sense that this is this and this is that, and that's why. For now, you'll just have to take my word for it that freezing and condensing are exothermic. Condensing, I think, is somewhat obvious. Freezing is obviously not that obvious. However, the surroundings actually increase in temperature just a little bit when something freezes. And if you really aren't sure, the opposite of freezing and melting is melting, and you certainly know that melting is endothermic, so therefore freezing must be exothermic. So, yeah, that should be pretty obvious. If it's not, well, you can deduce that pretty easily by making an obvious statement, and if it's not obvious, I don't know, do something about it. Uh, Nextly, now we actually go on to the meat and potatoes of this. The enthalpy change of a reaction. It's defined as the chemical potential energy change of a reaction. I think I see why they call it enthalpy now, because it's a lot less work to say enthalpy than it is to say chemical potential energy. But anyways, it's just the potential energy lost during a particular reaction. And we can quote it in kilojoules in joules, or often quote it in kilojoules per mole, where the per mole is referring to a mole of something. So the delta H of combustion of methanol is minus 727 kilojoules per mole. The mole there clearly refers to the methanol, or the potential loss in energy is that. However, when it's written beside a balanced equation, this per mole thing is omitted because the number of kilojoules is stoichiometrically related. So, for example, from this balanced equation, we can denote that 2 moles of this thing releases that much energy, or if you have 3 moles of oxygen, it releases that much energy. If you form 2 moles of carbon dioxide, you release that much energy, and then lastly, but similarly, you have 4 moles of water, you release that much energy. Or you can divide through by the coefficients there and get it in per moles of whatever reactant or product you're doing your measurements with respect to. And you can actually go one step further and work your way backward, and you say you have a certain amount of heat you want to release, but you don't know how much reactant to put into the system. So, for example, what is the delta H for burning 1.35 moles of that thing? We know that delta H, well, we'll go later on, but basically delta H is just the Q of the reaction, the amount of heat energy released to the reaction, divided by the moles of the limiting reagent. And typically, as is convention, if all the other reactants are not mentioned, it's usually the one that you're talking about is the limiting reagent. So it's just, uh, you know, so you know that for every 2 moles of methanol, you lose that much energy, as we just discussed earlier. So write out a conversion factor, and you get 981 kilojoules. Similarly, this one just involves an extra step. Number 2, what mass of oxygen would be consumed when enough methanol is burned to release that much heat. You know how much heat is released, so, and you also know that for every 3 moles of oxygen, you release that much heat. Just again, look at the balanced equation, rewind the video, I don't know, minute or so, and you'll see the equation. But anyways, so now that you have moles, you can just, multiply by the molar mass and you'll get the mass of oxygen you need. Lastly, here is more of an experimental setup that I think is worth going through. When you have 2 grams of that thing dissolved in that much water, initially at 24 degrees Celsius, once the dissolution was done, the resulting temperature of the solution was 23.22 degrees Celsius. Calculate the change in enthalpy for that solution reaction, assuming no heat loss or whatever. So first off, write a balanced equation. It often is helpful. Secondly, you want to get the number of moles of. Steps 2, 3, and 4 are interchangeable. It doesn't really matter in what order you do them, but in this case, the notes are written out in such a way that we calculate the number of moles first, and then we calculate the Q of the reaction, and then lastly we know that delta H is the Q of the reactions over the mole of the limiting reagent, which we can just pull that up. From previous parts that we've just calculated in there, and we get 4 kilojoules a mole. Here's another one. It's not worth. I'll probably go over a couple of these in a video worksheet at some point. And then lastly, standard enthalpy change of combustion. The standard enthalpy change of combustion is the enthalpy change associated with the complete reaction of oxygen of 1 mole of a substance under standard conditions. These are always exothermic, which that should make sense. Combustion releases heat, and you should know that because, if you ever burned something, fire is hot. I don't know what else to say, but yeah. Hopefully this one actually recorded. If it didn't, then fuck me. Thank you for watching. I forgot to mention that bit.